Okay, so the next sample problem that we have is going to be problem 16.5, and it is found on page 1131. Okay, so as we look at the problem here, what we have is we just have a simple disk. It's got a cord attached to it. And what we're going to do is this T represents a tension, a pulling force that we're just pulling on that cord to kind of unwrap it. And then that disc is going to, go in a circular motion around. And its center that we're referencing is going to be the center of rotation there, or the center of gravity of the actual disc itself. Now, as you can see here, this is not secured down. So this disc is kind of free moving, if you would, in the X and the Y direction. And that kind of makes a difference in how we set this up. So we'll see how that acknowledgement shows on our diagram. So the problem statement says a cord is wrapped around a homogeneous disc. Homogeneous just means that it's all of the same thickness and it is all of the same material. It's an even cross section throughout, okay? And they're giving us the mass of 15 kilograms. Also, you're going to notice that we are given the radius to the outside edge, if you would, of that disc. So instead of they're not giving us a radius of gyration this time, because this is, if you would, a simple shape, a disc, we'll be able to use the Cand equation for the rotational inertia. And I'll show you how we do that. And then the cord is pulled upward with a force of 180 newtons. They want us to determine the acceleration of the center of the disc. Okay, so that's going to be around G. They want us to also determine the angular acceleration of the disc and the acceleration of the cord. Okay, so I'm just going to jump right in, and we are going to go underneath here, and we're gonna start just like we normally do, identifying what we're given as well as what we have to find, and then we're going to draw our diagram. So this is sample 16.5. I'm going to put our convention in our upper right-hand corner. And what we are given. So we know that the tension in that cord as it's being pulled. Oh, I'm so sorry. No. The radius I have first. The radius is equal to 0.5 meters, and that is going to be the radius from the center of mass to the outermost. Okay, so, and it is in meters already, so we don't have to change anything. Our mass is equal to 15 kilograms. Gravity is going to be 9.81 meters per second squared. So the last two problems we did were the 32.2. Now we're 9.81. And again, I know they don't specifically give it, but I like to write it down just so that I have it handy and top of mind. And now the force being pulled on that cord, tension, if you would, in that cord is 180 newtons. Okay. So our units are going to be the meters, seconds, kilograms, newtons, for the metric system. So what we need to find, okay, is going to be the angular acceleration of the disk. Okay, so how fast is that going around? Or not how fast, what is the acceleration or deceleration of that disk? Should be acceleration because we're pulling on it. What is the straight line acceleration in the Y direction of the center of that disk? And we're going to look, what is the acceleration in the X direction for the center of that disk? And then lastly, what is the acceleration of that cord as we're pulling it up? Okay. So step number one, as we have been, we're going to be drawing our diagram. Okay. Even though this is a circular item, I'm just going to kind of focus on the center and just kind of draw a straight line. So we're going to start with at the center. This is going to be our center of gravity, G. And then out on the side here to the left, is going to be the tension in that cord equal to 180 newtons. We know that this radius is 0.5 meters. And we know that the weight of that disc is going down, right? The weight. Now, we can calculate that weight because we know its mass and we know what gravity is. So let's go ahead and do that. So I'm just going to do a little bit of note on the side here. So I'm going to say W is equal to mass times gravity. So that's going to be 15 times 9.81. So our weight is going to be 147.15 newtons. So this is going to be 147.15 newtons. So that's that. So these are our forces. Static side. We're going to set that equal to, okay? And now what we're going to do is we're going to look at that center, okay, which is G, all right? And when we look here at the center here, we see a force that we're pulling on it with, but when we look at the mass, we would put it at the geometric center, okay? And when we would, and that would be in any direction. So that means that we have mass times acceleration in the y times, yeah, mass times acceleration in the y, that's all that it is. So m(a)y, so it's the mass of the disk in the y direction. And then we're going to see in both of these directions, is there anything going on? So mx, okay? And then lastly, because this is pulling up, there is going to be a rotation, right? So this is going to be our angular momentum. So it's going to be the rotational moment of inertia of that. I'm not even going to put it. It's just of the disk times the angular acceleration. Okay. Now, if you're saying, why aren't you putting that in a, because if we're pulling on this disk up, right? And this is attached, the disk should be going in a clockwise direction. Why did you put it in this direction? I'm going to put it in that direction because it's a teaching moment. I'm going to show you that if you put your direction or forces on this side or this side in the wrong direction, you're going to end up with a negative value. Okay. And then you'll know that you have to change it. So we're going to find in our math, it's going to let us know that we didn't do that correctly. Okay. So that's the reason for it. So I'm actually intentionally putting it in the wrong direction so we can correct it along the way. All right. So just in case you notice that. All right. So now that we have our diagrams done, our step number 2 is going to be our motion equations. Okay. So we've always got 3. So we're going to sum our forces in the x equals mass times acceleration in the x. So sum the forces in the x on this side is equal to m times ax. So if we go on this side, what are we going to write for sum of the forces? There are no forces in the x direction. So that means this is going to be 0 is equal to max, which means that our acceleration in the x direction is equal to 0. Okay, so it just kind of proves that. So honestly, if I would have been drawing this and you would have noticed there's nothing in the x, you could just leave this off. Okay, you wouldn't even have to put that on, but it asked for us to find the total acceleration, which x is one of the directions. So this is equal to 0. So this is one of our answers. Okay. So now we're going to do that same thing in the y direction. Now you'll notice that we have stuff going on in the y, so we're probably going to see something in that direction. Okay. So let's do the sum of the forces in the y is going to be equal to mass times acceleration in the y. Okay, and that's what we have, you know, here on either side. So force is in the y. We've got a positive 180 and a negative 147.15. So we've got 180 minus 147.15 is equal to, now we know that the mass is 15, right? And then acceleration in the y. So our only unknown here is acceleration in the y. So we can solve for it by dividing both sides by 15, and you should get your acceleration in the y equal to 2.19 meters per second squared. Make sure you put the units on there because this is one of the final answers that we need. Okay? So we've got a y acceleration. Now, why do we have a y acceleration? It is going to move in the y direction. And the reason is because remember when we looked at the disk, there is no support here holding it in place. Okay, so it's just kind of free flowing. We're going to pull on this and this is going to kind of twist and go up. Okay, as it's like if you would laying on the ground. So there is an acceleration there. Okay. Now it's also going to be rotating around. So our last equation, I don't think I'm going to fit it on here. So what I'm going to do is go here. Actually, do something like this so we can see the diagram as I write out the problem. Okay. So I'm going to do the sum of the moments around that center of mass, G, is going to be equal to rotational inertia times the angular acceleration of the disk plus mass times acceleration times our distance perpendicular. Now, remember we're summing around G, so that's our center. So even though we have acceleration here, you might be like, well, don't I have to put the AY in here because there was an acceleration? It is going through the center of the point. So there is no offset distance. That goes to 0. So we do not do any part of this part. It's only going to be purely rotational. Okay? All right. So again, it's because there's no perpendicular distance. So let's do our moment first. We're going to put our finger on G. Our offset force is going to be the 180. And its offset distance is times 0.5, right? 0.5 meters. And then it is going to rotate in a clockwise direction. So negative out front. Negative out front. The W does not get included because if I put my finger on G, it's just going to pull. It's not going to rotate. Okay. It's going to be equal to. So now I have my rotational inertia. Okay. My rotational inertia, to calculate that, I need to use the information that was given to me up in my problem, which was the radius and the mass. So this is a disk. If you recall, on our sheet here, we did write this one down for this purpose, okay? So it's going to be equal to 1/2 times the mass times the radius to the outer edge, okay? If I go back in my PowerPoint presentation, and you can also, these are standard equations. You could look these up by just doing a quick search. But right here, these are the standard equations, and this is a solid cylinder, so it's 1/2 mass times the radius. And I know you can't really see it very well on this thing, but it's from the center of rotation to the outer surface, and we're going to square that value. Okay, so go back underneath here. So we're using this equation. So over on the side, I'm just going to go over here where I is equal to 1/2 mr squared. So that's going to be 1/2 times 15 kilograms. And that was given to us again in the problem. And then our R is times 0.5, and don't forget to square that value. So our I is going to be 1.875. And that'll be the number we use up here. So 1.875 is going to be our I times the angular acceleration. Okay, so that's going to be our unknown value. All right. So now when we do this, we're going to divide both sides by 1.875, and we're going to get a negative 48 radians per second squared. Those are the units for angular acceleration, and that's something we learned back in kinematics. Okay. I do have a place on my equation sheet that I have units. So after we're done with this problem, I'll pull up my equation sheet, and then you can make sure that you have all the standard units for everything down. And this is one of them that's on there. So radians per second squared is going to be equal to our angular acceleration. And this is the disk. Okay, this is the disk. Now, notice the negative up front. This was what I was talking about earlier. Angular acceleration. As we look at our problem, this could mean, I mean, you could say, well, doesn't that mean that it's decelerating? Well, let's think about the problem. And this is where you got to use your noggin a little bit. So if we are starting from rest and we are pulling on this, this is going to speed up. So the negative being there is not slowing down. Okay. So we are going to be speeding up, and if we look here, if we pull in this direction, the angular acceleration has to go in that direction. So we're just going to change the direction of our rotational inertia here, and we are going to remove the negative. So just put a positive out front or erase it. Okay, so do not leave that answer with a negative in front of it. And then you're going to put a box around, and this is going to be clockwise. And that takes care of this one. Okay. The last acceleration we have is going to be the chord. Okay, it's going to be the chord. All right. So now I'm gonna draw a little illustration just to kind of isolate and just look at the acceleration portions without the masses and such in there. So I'm going to, let's see, 3. This is going to be acceleration of the chord. Okay. So I'm going to have my G. And then out from there, I'm going to have the acceleration of the chord. Okay, acceleration of the chord. Now, the acceleration of the chord has 2 accelerations. We have an acceleration y that we saw here, okay, and we have a value 2.19 that we calculated, right? So this is equal to 2.19, and this is meters per second squared. And then the chord out here there is a tangential acceleration due to the angular acceleration and the radius of 0.5 meters. So this would be the radius RA, or I don't know, it's not A, this one's not A, I don't think. This is just the radius, 0.5 meters, okay? And we know this angular acceleration is 48 radians per second squared, okay? So the acceleration of the chord is going to be that tangential value plus this y, because remember, this is not attached at the center, so it's not only going up due to the pulling of the cord, but this is also going up at the same time. So there's two accelerations that are adding together on the cord. So the cord is going to be equal to this tangential out here due to the angular acceleration in that radius plus the AY. Okay. So our tangential is going to be equal to the radius times the angular acceleration plus the, what was that value? 2.19. Okay, so I'll put these values in. This is going to be 0.5 times 48 plus 2.19. So the acceleration of our cord total is going to be 26.2 meters per second squared. And that's going on. Okay. Does that make sense to everybody? If that center was fixed and this was not having the ability to go up along with the disc, then it would only be that tangential value, okay? But because it's not attached or fixed at that center, you're gonna pull and it's gonna come with you, okay? So those two add together. I hope that makes sense, because I had to look at that a little bit. I'm like, wait a second, but it's because it is not attached or fixed at that center, okay? Right. So that's our third and final example this evening, and it's our third and final practice problem for module 2 and chapter 16. So let's take a peek at where we're at in our PowerPoint. We should be, actually I pushed up there. We should be all the way at the bottom here. This was assignment, or this was sample problem 16.5. So now we've completed these practice problems and you're ready to start looking at application problems. So let's take a quick peek first at the practice problems for module 2. If we look back, you'll remember that in chapter 12, the last time we were together, we did 3 problems. Okay, so those 3 are included. And then this evening, we did the 3 that we see here. Okay, so now we have, completed the ones that I wanted you to get used to the equations, the concepts, and kind of set you up for doing the application problems. So you're ready, to hand those in once you have all the final details there. Application problems. Okay, so as we had talked about last time, the first 3 problems here are ones that I made up, and these go along with the chapter 12 problems. As I had stated, I didn't find any that I really liked that I felt that they had at the end of the chapter or in that chapter that went along with the application problems or the sample problems that they had. So I did my own. So those 3 you will complete based on the information here. And we went over those the last time. The 3 that you're going to do in chapter 16 are listed here at the bottom. So 16.9, 16.33, and 37. Okay. Now the final answers are here for you. I wanted to also let you know that if you have any questions on this homework assignment, the next time that we're together, I have time set aside to go over anything that you have questions on, okay? But in the meantime, if you're like, you want to start getting going on the application problems, you cannot wait until Monday. I don't blame you. If we look in our session recordings, okay? The last time that I did this course, so right now for the recordings for spring 2026, you'll notice that we have the chapter 12 sample problems. I'm going to be adding the chapter 16 right below here that we did tonight, but I have 3 videos out here for homework help, and these are specific to problems 16.9, it's setup, problem 16.33, setup, not the whole problem, just the setup, but then number 37 is pretty much the whole problem, okay? So I encourage you to go out, get those going. And if you do have any questions, take a peek at these, and they're out there. But I will also be happy to go over and through anything that you want to the next time that we meet on any one of these problems. And that includes the chapter 12 ones as well, okay, that you have assigned. So are there any questions before I, stop recording here based on the homework and the practice problems for module 2? Okay, not noticing anything. So I am going to stop the recording here.